In this chapter, we begin with a very important question: why is BIM considered a construction best practice? Traditionally, construction projects were managed through many separate pieces of information. Architects had their drawings, engineers had their drawings, contractors had schedules, estimators had cost information, and project teams often communicated through separate channels. When information is separated like that, it becomes easy for conflicts, delays, and cost overruns to occur. BIM changes this situation by bringing project information together into a shared digital environment. Instead of treating design, schedule, cost, and coordination as separate activities, BIM allows the project team to connect them in a more integrated way. So, the key point is this: BIM is not valuable simply because it creates a 3D model. BIM is valuable because it helps the project team plan, coordinate, estimate, schedule, and build with better information. It helps move the project from fragmentation to integration. Before BIM, many disciplines worked in silos. Updates were often manual, conflicts were discovered late, and field surprises could become expensive. With BIM, information can be more coordinated, errors can be reduced, transparency improves, and the overall project outcome becomes more predictable. One of the most common misunderstandings about BIM is that it is just software. Many people think BIM means using programs such as Revit, ArchiCAD, or another 3D modeling platform. These tools are important, but they are not the same thing as BIM itself. BIM is better understood as a process. It is a process for creating, managing, sharing, and using building information throughout the life of a facility. That life cycle can begin with early planning and continue through design, construction, operation, maintenance, and even demolition. This slide shows that BIM sits at the intersection of three major areas: policy, process, and technology. Policy includes contracts, standards, project requirements, and the BIM Execution Plan, or BEP. These documents define how BIM will be used and what the project team is expected to deliver. Process includes collaboration, coordination meetings, leadership, communication, and information exchange. Without a strong process, even a good model may not be used effectively. Technology includes modeling software, cloud platforms, data systems, and computer hardware. Technology supports BIM, but it does not replace planning, communication, or management. For construction managers, this is the important lesson. BIM is not mastered simply by learning software commands. BIM becomes powerful when digital information supports communication, coordination, decision-making, and project control. Construction management is often focused on three major areas: cost, schedule, and quality. BIM supports all three by turning the 3D model into a central hub of project information. First, BIM supports schedule management through what we call 4D BIM. In 4D BIM, model elements are linked to schedule activities. This allows the project team to see the planned construction sequence visually. Instead of only reading a list of activities in a schedule, the team can review how the building will actually be constructed over time. This is useful because it helps the team identify sequencing problems, trade overlap, site access issues, delivery conflicts, and equipment location concerns before the work begins in the field. Second, BIM supports cost management through 5D BIM. In 5D BIM, model elements are connected to quantity and cost information. For example, the model may help organize quantities for walls, doors, windows, structural elements, or MEP components. When the design changes, the estimating team can review potential cost impacts more quickly. However, it is important to remember that BIM does not automatically create a complete estimate. Professional judgment is still needed for labor productivity, means and methods, market pricing, subcontractor quotes, waste, risk, and other cost factors. Third, BIM supports quality management through coordination and clash detection. In a coordinated model, architectural, structural, mechanical, electrical, plumbing, and fire protection systems can be reviewed together. Hard clashes, such as two systems occupying the same space, can be detected. Soft clashes, such as missing access or maintenance clearance, can also be identified. This allows construction managers to shift quality control upstream. Instead of discovering problems after installation, the team can resolve many conflicts virtually during pre-construction. This slide compares traditional design and construction with a BIM-based process. In a traditional 2D workflow, architecture, structure, and MEP information are often developed in separate drawing sets. These drawings are essential, but they can become difficult to coordinate when a project is complex. For example, if the mechanical engineer changes a duct layout, that change may also affect structural clearance, ceiling height, lighting layout, and fire protection systems. In a traditional workflow, these updates may need to be made manually across several different drawings. If one update is missed, inconsistencies can occur. These inconsistencies often lead to RFIs, field revisions, change orders, and late changes during construction. The problem is not that 2D drawings are useless. The problem is that disconnected information makes coordination more difficult. BIM replaces this fragmented process with a more integrated approach. First, BIM supports a single source of truth through a common data environment, or CDE. This allows project information to be shared, managed, and reviewed in a more coordinated way. Second, BIM supports automatic updates. When model information is properly developed, changes can be reflected across related views, schedules, and quantities. This improves consistency and reduces the risk of missed information. Third, BIM encourages early decision making. Instead of solving problems in the field where changes are most expensive, the project team can identify and resolve many issues during concept, design, and pre-construction. That is why BIM is considered a best practice. It helps teams solve problems earlier, coordinate more effectively, and reduce the cost and disruption of late field changes. This case study shows how BIM can create real value in a construction project. The project was a large public educational facility in the southern United States. It included more than 430,000 square feet of laboratories, study spaces, and an auditorium. The project was delivered using a construction manager at risk approach, which means the construction manager was involved before construction to help manage cost, schedule, constructability, and risk. On a project of this size, coordination is extremely important. Mechanical, electrical, plumbing, fire protection, structural, and architectural systems all need to fit within the same building spaces. If these systems are not coordinated early, conflicts can appear during construction. A duct may conflict with a beam, a pipe may interfere with ceiling space, or one system may block access to another. To reduce these risks, the contractor used BIM during pre-construction. The project team brought separate discipline models together into a federated model and reviewed the building floor by floor and system by system. When conflicts were identified, the affected team members discussed possible solutions and updated their models. This allowed many issues to be resolved before materials were ordered and before labor was committed on site. This is sometimes described as building the project twice, first virtually and then physically. The virtual model does not replace field construction, but it gives the project team a clearer understanding of the building before construction begins. The results shown on this slide highlight the value of that approach. The BIM coordinated process reduced structural change costs compared with traditional methods, generated significant savings, and produced a strong return on investment. The broader lesson is that BIM shifted the team from reactive problem solving to proactive planning. Instead of waiting for problems to appear in the field, the team identified many of them in the digital model and used that information to improve coordination, reduce rework, control schedule impacts, and deliver a higher quality project.